All right, so this video is going to be an example of a practice problem of a one-dimensional situation. Now remember, why would we do a one-dimensional situation? Well, 2D motion is just X motion independent and Y motion independent. So really we just have to get a little bit more comfortable with our one-dimensional motion and then be able to combine them in a couple ways. So in this example, we'll be shooting a water balloon straight up into the air with an initial y velocity of 60 meters per second. And we're going to consider when the balloon leaves the launcher, it has a position of y equals 0 meters. So just as soon as it leaves there, we're going to start that as our origin going up. Throughout this video, you're going to be asked to answer a few questions. You're actually going to go ahead and answer the questions before I do them. And you won't be graded on this. It's just to check where we're at. So there's going to be some questions along, and yeah, so just answer those as I go through. Before we start, let's go ahead and put some equations on this piece of paper that are going to be pretty helpful. Remember that when we have uniform acceleration, which in the y dimension, in projectile motion, we do have uniform acceleration because we only have gravity acting on the object. We know that the acceleration equals to the change in velocity divided by time. We also know that the change in velocity equals acceleration multiplied by time. That's just a rearrangement. These two only have velocity, acceleration, and time in them. The one other equation that's really important is going to be the one that is going to help us with displacement, or how far something moves. In that equation, our displacement equation is the initial velocity multiplied by time plus 1/2 the acceleration times time squared. This is going to be a really helpful equation in this worksheet. So let's get right to it. Draw a force diagram for the balloon after it has left the launcher. It should say launcher. So once it's left the launcher, remember the force diagram only has the force due to gravity. Sorry, it's a crooked line, but it should be straight down. And that's just going to be the mass of the balloon times the acceleration due to gravity. But the only force that's acting on it is this downward pull by gravity. It's the only thing. So there's no acceleration in the x direction changing it. It's only being accelerated in the y dimension. So that's your first one. What is the acceleration of the balloon? Go ahead and answer this. Okay, so if the force is only due to gravity, then the acceleration, it's in the y dimension, so we'll put a little y there, and it's equal to 10 meters per second squared, but we need to be a little more clear. We're going to say negative because negative is going to point down. Gravity is always going to point down. We're going to choose our upward motion to be positive and our downward motion to be negative. So acceleration is 10 meters per second squared. All right, calculate the time required to reach an upward speed of 30 meters per second. So if we go back and we look at our initial velocity was equal to positive 60 meters per second. The positive sign is just saying it was upward. The 60 meters per second is the magnitude. So calculate the time required to reach an upward speed of 30 meters per second. Well, 60 to 30, there's a change in velocity. So that means that there's some acceleration. Well, we just said that the acceleration equals negative 10 meters per second squared. So if you use your equation, you want your change in velocity, which is final minus initial. So positive 30 minus 60 equals the acceleration times time, negative 10 times t. Well, positive 30 minus 60 is negative 30 equals negative 10 t. Divide by negative 10, divide by negative 10, and you get t equals 3 seconds. Now that was a lot of math there, but if you just look at this, it started at 60, every second it's losing 10. Well, of course, in 3 seconds it would be at 30. So there's a quick way to answer that one if you don't want to do all this math, but it just double checks that it's correct. So it'll take 3 seconds to have a speed of 30 meters per second because you're losing 10 meters per second every second. Okay, now calculate the time required to reach a downward speed of 50 meters per second. So it's saying when we're going to call that our velocity equals negative 50 meters per second. And this is a question where your positive and your negatives are going to be very important because we are dealing with an up and down situation, so we need to be really clear what's positive, what's negative. So the velocity here will be the negative 50 is what we're looking at. We know that, again, our initial was positive 60 meters per second. And we know that our acceleration equals negative 10 meters per second squared. All right, so those are the 3 pieces of information, and we're looking for time. Well, we know our change in velocity, or final minus initial, final, make sure you put your negative sign, minus your positive 60 equals negative 10 times t. Now check out what number we're going to get here. Negative 50 minus 60. Well, that's going to be negative 110. And let's just, I'm going to put my units on there. I'll put the units back on here. If we look at this negative 110, it's a really important number. It's actually saying the total change from an upward 60 to a downward 50 was a total of negative 110 because you had to subtract all the 60 to get to 0, and then you had to go another downward negative 50. So it's 110 in the negative change. If we divide that by negative 10, divide that by negative 10, we see that t equals 11 seconds. So it'll take 11 seconds to reach a downward speed of 50 meters per second. All right. So this is going to be really useful when we get a question like this. Calculate the time required to reach the max height. Well, at the max height, we know this very important fact. And I'm not going to give you this fact every time from here on out. So just remember that when it reaches the max height, the velocity in the y is 0 because it's gone up, it stops, and then it comes back down. So you need to remember max height means velocity in the y 0. So the velocity equals 0 meters per second. Again, the initial was positive 60 meters per second. Our acceleration is negative 10 meters per second squared. And our time is unknown. So we see that if we put this in our equation, we have final of 0 minus 60 equals negative 10 times t. Divide by negative 10, divide by negative 10. Sorry, 0 minus 60 is just negative 60, so that just goes away. And we get t equals 6 seconds. Again, you don't have to do this math. You can just look. If it's going 60 in the positive direction and it's going to lose 10 meters per second every second, then yes, it's going to take 6 seconds to slow down to 0. So if I asked you after 1 second how fast is it going? 50 in the positive. After 2, 40. 3, 30, 20, 10, and after 6 seconds, it's going to be going 0 meters per second in the positive direction. So we get that 6 seconds to get to its max height. Okay, now we need to calculate the max height. So go ahead and give it a try. Okay, so now max height includes a new value that we haven't been talking about. It's talking about the displacement. How high, and actually in this case, usually we write displacement is x, right, plus 1/2 a t squared. And this is a great point here. This equation, to be a little more specific, now we're doing it in 2 dimensions. To be a little more specific, the change in x is the initial velocity in the x, and you have to also consider the acceleration in the x. Time doesn't actually have dimensions here, so time is going to be the same in both dimensions. So you just need to be clear that here it's the x and here it's the x. Well, we're going max height. So actually we're going to rewrite this equation, the exact same equation, but just flip around a couple variables so it makes a little more sense for our situation. We're going to say the change in y equals the initial velocity in the y times time plus 1/2 the acceleration in the y times t squared. So this is a better fitting equation when we're calculating max height. This would be an equation to figure out how far something's gone in the x dimension. Okay, so a couple other things we need to know. Well, we know our initial velocity in the y. We've written this before. We didn't use this notation, but you can use this as to be really clear that this is initial and it's in the y. Let's write that. Initial and y dimension. That's all it means. Keep it organized. That was positive 60 meters per second. We just figured out in this last one that the time it takes to get to the max height is 6 seconds. So we can use that as our time here. If we're saying where's it going to be at after 6 seconds? So after 6 seconds, if we use the equation, we should be able to find that delta y. And we know the acceleration in the y. Again, we didn't use this notation before, but that just means it's in the y dimension. Equals negative 10 meters per second squared. So we have all the pieces to solve for this delta y. Let's go ahead and plug them into our equation. Delta y should equal positive 60, I'm going to drop my units, times 6 plus 1/2 of negative 10 times 6 squared. All right, let's see if we can do this. Well, to rewrite it and simplify, 6 times 60 is 360 positive plus, we know that this whole term will be negative because there's a negative sign here. So let's do it here. It's going to be 6 squared, which is 36, plus, or multiplied by 10, which is negative 360. But then we need to divide it by 2, which is, let's see, 150, 130, negative 180. So we have 360 minus 180, and that's going to give us a change in y of positive 360 minus 180 is positive 180 meters. There you go. So the change in y from when it left the launcher to its max height was positive 180 meters. Great. Okay, and then calculate the time it takes to return to its original height of y equals 0 meters. We'll go ahead and do that one. All right, now you should be able to look at this one and actually do it very quickly. There's a couple ways to think about it. You can do it a math way, you can do it with a picture as well. We know that the path of this is going to be up and then it's going to come right back down. Now, we talked in 2D motion that if it had an initial x, it would make somewhat of a parabola. Well, if we're just looking at how it moved in the y, it still kind of has that symmetry, meaning that it will take the exact same amount of time to get to the top as it does to get to the bottom. So right away we can say that t, I don't know what you want to call it, t max height, so the time it took to get to the max height was 6 seconds. So the t total, or original height, right? Original height should be just double that. It's 12 seconds. Now those are really long subtexts there, but just to be sure that we're talking the time it takes to return to that original height, up 6, down 6. There's a couple other ways that we can figure it out. We can use a lot more math, but basically if you figure out how long it takes to get to the top of the parabola, you can always figure out how long it's going to take to get to the bottom, because it's just going to take the exact same amount of time. Now, just quick word again. This was not the path of the balloon. This would be if the balloon was shot at some angle and it was given an x and a y. But remember, we're moving into this idea that now it will have, in some future questions, we are going to give it an x and a y. But you can do everything we did in this video in the y dimension. Separate everything into its y dimension and its x dimension. So this is a little practice to get us back into that groove of using one-dimensional motion in the y dimension.